Hi, am I audible? Okay, so so Subrata here, and I am your teaching assistant for the thermal physics course taken by Professor Demal Banerjee in this semester's NPTEL. So, and I am a PhD student in the Department of Physics at IIT Kanpur. So let's start. And okay, so first share my screen. Okay, so my screen is visible now, right? Okay, so today I will going to discuss the week 5 content. And okay, so first we discuss the last class parts. Okay, so what we discuss in the last class, that briefly about Brownian motions, okay, and specifically discuss that how the irregular movement. So 1 minute. Yeah, so yeah, so we discussed in the last class that that how the irregular movement, how the irregular movement of particles suspended in a liquids, suspended in a liquid related to the diffusion equations, related to the diffusion equation, right? So these questions, and we make some assumptions that each particle movement independent of the other particle movements, and second, the movement of one or same particles after a different interval of time. So we consider a certain interval tau. So we consider a time interval tau. So in and two subsequent time intervals, okay, are independent. Okay, that means the particle traveled a distance delta in each time intervals independent of the other time intervals. Okay, so then this delta, the particle distance traveled in this time interval, follow some distribution is the phi delta, right? And so this is a probability distribution, and we make also the further assumption that phi delta goes very rapidly. Okay, so that means it's differ from zero. It differ from zero. Okay, for small values of delta, for small values of delta, right? So when delta is small, then only phi delta 0. Okay, and delta is large, then the phi delta is goes to 0. So then we can use Taylor extensions, and finally we get this equation that del phi delta t equals to d times del to f. So this both x and t, del to f delta x2, right? But d is a diffusion constant. So we make this kind of following assumptions, we get end up with these equations. Okay, so where d is this d actually the diffusion constant, diffusion constant, right? Okay, so these equations, okay, so this equation describe describes describes the evolution of the distribution of a particle in space and time, right? So it's also time dependent. So how evolve with time and related to the evolve with space, right? So this del f del x2, this is the derivative with space, and the left hand side is derivative with times, right? So they are related via diffusion constants, right? So and then we solve this equation using the Fourier transform. We go into the Fourier space, and the solution of this is the distribution functions. Distribution functions is that f of xt. The solution is that the n is the total number of particles, root of 4 pi dt time, and e to the power minus x square over 4 dt, right? So this is the solutions. So then we can calculate x average. So we know, once we know the distribution functions, we can calculate x average. Okay, so simply that some x f of xt dx, right? And by normalization factor. Okay, so it's n. So once you normalize the thing, that means that f of xt dx over the whole range. Okay, so minus infinity to infinity, minus infinity to infinity. So we get a 0. Okay, so because this f of xt is a even functions of f of xt is a even functions of x, and when you're calculating x is a odd function, so even odd on the full range. Okay, minus infinity to infinity, we get a 0. So similarly, we calculate the x square average, right? So we get a 2 dt, right? So in the previous class, I will calculate these things. Okay, so x square average is 2 dt, right? And then so these 2 dt, and we say define this lambda x is actually root of x square average. This is a RMS length, okay, because RMS length is that actually the x RMS or lambda RMS is root of x square average minus x average the square, right? So since the x average is 0, so is only x square average, so this is actually root of 2 dt. So this is the typical characteristics of the Brownian masses. So this is the typical characteristics of the Brownian mass. Motions. Okay. So these things we discussed in the last class. Okay. So and any questions on this? Okay, good. So then so today I'm going to discuss that what is the physical interactions. Okay. So what is the theoretical observations of this, that this lambda x is equal to 2 dt? Okay. So then we first we have to understand that what do you look in the physical point of view. Okay, so that means what this means is a physical, that that the irregular movements. Okay, so the irregular movement of the suspended particle in a liquid, the suspended particle in a liquids are caused by thermal motions of the molecules in the theoretical point of view. Okay, now physically this irregular movement of the suspended particle in a liquids are caused by the thermal motions of the molecule. The thermal motion of the molecules, right, of the liquid, of the liquid, right? So what kind of thermal motions? And so these thermal motions of molecules, okay, so these thermal motions of molecules give actually the due to this thermal motions of molecules, there is the existence of random force. So existence of random force. So due to these thermal motions of this molecule in the liquids and the existence of the random force, and due to this random force the bounding motions can be happens. Okay. So okay, so let's do one example so it becomes more clear. Okay, so suppose that we impact to a particle. Okay, so let's write it down. So suppose that we impart to a particle suspended in a liquid, impart to a particle suspended in a liquid certain velocity v. So this is the assumption. So first assume that we impart a particle in a liquids with a velocity v. Okay. So certain velocity is v, right? By a force, let's say by a force applied to it from outside. Okay, so applied to it from outside. So we assume that. We impart a particle in a liquids, okay, suspended liquids with a velocity v by adding a force from outside. So first let's take these assumptions. Okay, and so this velocity so die out rapidly due to the friction of the liquids, right? So when you put in the liquid, so due to these frictions of these liquids, this molecule, so this velocity die out rapidly, right? So this velocity, so then so this actually tells that the Stokes law, F equals to minus 6 pi eta r v, right? V is the velocity and this is the drag force, right? So there is a drag force applied on the particles, and due to this velocity die out rapidly, right? So where is eta actually the viscosity of the liquid? So it's the viscosity, v is the velocity, right? And r is the radius of the particle. Radius of the particle, right? So this equation tells that that there is applied on drag force in opposite to the particle velocity. Okay, and due to this the particle velocity die out rapidly. Okay, so and we solve these equations. We just put this f actually m dv dt. Okay, and once you solve this is the first order differential equations, easy to solve. So it's v0 and exponential minus 6 pi eta r by m into t, right? So v0 at t equals to, so at t equals to 0 we impart a velocity v0 by external source. Let's say by external source we put a particle with velocity v0 in the liquids, and after certain time t this velocity v, okay, is exponentially decaying. Okay, so that means so particle loses its original velocity completely, nearly completely in very short time, okay, through friction, right? But what do we know from the kinetic theory? So that means that the particle velocity after certain times die out, right? But what do we know from the kinetic theory? But what we know from kinetic theory? So up to this point is clear? Or any question? Okay, so kinetic theory. So in Maxwell kinetic theories, okay, so we can calculate the mean value of the instantaneous velocity, okay, which is particle may have at the absolute temperature T, right? So we calculate the mean values of the instantaneous velocity of the particle at, let's say, at absolute temperature T, absolute. Okay, so at a fixed, so this is a fixed Okay, so at absolute temperature T, the instantaneous velocity, this means that half m v square, and that average. What is this? Kinetic theory tells that this value is. Can you tell me what is the value for this from kinetic theory? So in 3 dimensions. Okay, so particle move in any dimensions, and for each mode there is a half kmt, right? Okay, so let's make this. What is this value from kinetic theory? Okay, so from equiperson's theorem, what is this? No, I am considering E average. Yes, 3 by 2 cavity, right? So this is from equiperson's theorem. From equipartition theorem, right? So now this E is only kinetic energy, right? There is no potential energy in the Maxwell, in the kinetic Maxwell Boltzmann theory. So this E actually the kinetic energy, right? So E actually is kinetic. So it's half m v square. In general, v square, right? So it's, I am considering 3 dimensions. So vx square plus vy square plus vz square. So all are at. Okay, so this is actually v square, right? So that means just a half m vx square, vy square, vz square, and each mode vx square gives a half cavity, vy square also gives a half cavity, and vz square also gives a half cavity. That's why this is 3 by 2 cavity. Okay, so then we can calculate. Then I just put into this. So that means half m v square average is 3 by 2 cavity, right? So m just a constant taken outside from the average. So then we know that the v square average is 3 cavity by m. It's the known formula. Okay, so if you calculate the v average also, right? So if you calculate the v average from Maxwell Boltzmann distributions, you get some 8 kt by kbt by pi m something. So that means that v square root of this v square average. Okay, so we will not written this thing because we are only considering not any distributions. Okay, so just equipartition theorem. So what is this value? This just gives a v square average is 3 by 3 kbt by m. Yeah, so root of v square average is that root 3 kbt by m. So when temperature at a particular temperature, that means temperature is not equals to 0, m is not equals to 0, and kb is the Boltzmann constant not equals to 0. So this quantity is not equals to 0, right? And this is a constant value, right? At a particular temperature, it gives a constant at certain temperature T. At certain temperature T, right? So it vary with temperature. So when we fix the temperature, this value is constant, right? Okay. But we see in this case here. Okay, so the V actually rapidly fall down. Okay, so that means, so this tells you that there is some kind of random force, okay, due to these molecules. Okay, and due to this random force, okay, so gives the extra contributions. That's why that and makes that v square, this is non-zero, right? So therefore, to maintain the average, so written is clearly that therefore to maintain the average, root of v square average. Okay, to maintain the average, that means this quantity. Okay, the particle must experience impulses from the liquid molecule from the liquid molecules whose direction and magnitudes are random. Whose direction and magnitudes are random, right? So there is no specific directions and no specific magnitude. It's some kind of random fluctuations. Okay. So due to this, so that is actually to, before that, what is the existence of the random force? Okay. So we assume that there is some kind of random force there, and due to this to maintain the average square error. Okay. So experimentally observe this thing. Okay. So experimentally observe this thing that x square is actually proportional to x square average. Indirectly tell that x square average and the square root, that means lambda x is proportional to time. I think, yeah, so it's proportional to t to the power half. Okay. So we'll derive this. Okay, so we also this actually seen that from the this distribution functions. Okay, so if of x this kind of distributions, and we see that this lambda x is proportional to square root of tail. Okay, but we are going to the physical interpretations. Okay, so what kind of random force actually gives that? Okay, and which limits? Okay, so we will see explicitly here. Okay, so up to this point is clear, right? So to maintain this average, the particle must experience impulses from the liquid molecules, and we call this kind of impulses called the random force. Okay, so okay, so this thing we will later. Okay, so I mean that there must exist a random force f of t acting on each particle okay, so acting on each particle such that f of t average is 0 and f of t the square average is not equal to what is. So that means that if we consider a random fluctuations and this average, so this average over a long time period. So this is a time average. So just simply is a time average. Okay, so average over a long time. That means the average over a long time. Okay, so let's consider this kind of distribution, that particle is fluctuating. Let's say these kind of distributions. Particle, let's say, fluctuating in this way. Okay, so over average we get a 0, but when we calculate ft square, that means this goes to the positive. Okay, so ft square, that means what kind of distribution? This kind of things, right? Sorry. So it gives a positive value, right? So then this average is not equal to 0. So this is a 0, but this is a not equal to 0, right? So when you make a square, that means negative goes to positives. Okay, so this is your x-axis. This is your time, and this is your ft. It's a random force. Okay, so they can take any value, positive, negative, fluctuating around 0. So over a long time period t, okay, over a long time period, this goes to 0. The average value, this 0 must be, because the any random kind of force, you have taken average over a long time, it will get a 0. But when it's square and then we take an average, so ft square average, okay, so this is not 0. Okay, so then this thing, so therefore this is the, okay, so therefore the equation, so this equation What is the equation? Yeah, so this equation becomes modified due to this random force. This is not the case, right? So this is not the case, right? So then this equation becomes modified, and the modified equation, thus the modified equation of motion is a derivative force minus 6 by eta rv plus f of t. So this is a random force. We just add a random force on this equation. Yeah. So this is just for clarifications. This is free from any external force. Free from any external force. We are not putting any external force. So previously I said that if we impart a particle with a velocity from external source, so that is from the assumption that we first to consider this, but this velocity actually comes from the temperatures, right? So when we hit the temperature, and the molecule get movement, right? So that's why. So this is an internal motion. Okay. So when we connect with the systems, okay, with a heat bar at particular temperatures, and due to this temperatures, okay, the particle movements allow, and due to this movement, this velocity is that. Okay, and the velocity cannot die out rapidly. Okay, so due to this random force, and this is from any external force, free from any external force. Okay, and this is the so this is the Langevin equation. So this is the so Langevin equation. Okay, so this is the Langevin equation. So this is the Langevin equation. Okay. And we solve this equation from and we get this exactly same value. Okay, so this x square average this 2d. So you get exactly same value when we solve this equation. Okay. So we will do this. Okay. So that's the okay. So up to this point, any questions? Okay. So then okay. So therefore we make that things that okay. That's the perpetual motions. That's the perpetual motion of the Brownian particles. The Brownian particles is maintained by the Brownian particle is maintained by the fluctuation in the collisions. Fluctuation in the collision, okay, with the molecules of the surrounding liquids. The molecules of the surrounding liquid, right? So this random force actually comes from the collisions with the other molecules, okay, in a bulk. Okay, it's maintained, right? And this actually maintained by the Brownian motions. Okay, the perpetual motions of the Brownian particles. is actually caused by the fluctuations of the collisions with the other molecules in the bulk. Okay, so we take that this fluctuation is a kind of random force. Okay, and we make assumptions that so assumption is that the ft is independent of the velocity, is independent of the velocity, right? So whatever the velocity is, this random force is always appears, right? And over a long time ft, this will be 0, and this. And second, that ft varies extremely rapidly compared to the variation of the velocity, right? So the velocity slightly changes, but ft can uh, oscillate very rapidly. Okay, so ft varies extremely rapidly compared to the variation of the velocity, compared to the variation of the velocity. So ft is independent of the velocity. Whatever the velocity is, the random force is always be there, and this random force is vary extremely rapidly compared to the variation of the velocity. So in variation, the velocity slightly changes, but ft can make a oscillate rapidly. Okay, so that means actually means that the second assumption actually tells that suppose we choose a time intervals. We choose a time interval tau. So in this time interval tau, the variation of the velocity is small, right? So variation of the velocity small, okay, but ft may undergo many fluctuations. T may undergo many fluctuations. Okay, so in these time intervals, ft may undergo many fluctuations. Okay, okay, good. So there is also define, if we define the correlation times. Okay, so later if I get times, then I can talk about what is the correlation. So correlation, fluctuation, etc. Fluctuation, correlation, fluctuation, and fluctuation-dissipation theorem. So these things later I will discuss if I get a time. So the correlation time is, so in this point I make a comment that what is the correlation time. So correlation time, it's a tc. Okay, so this is the minimum time in which this random force ft changes appreciably. Okay, changes appreciably. So this is the minimum time when the in which the ft changes appreciably. Okay, so that is the correlation time. Okay, so we'll discuss later what is that exactly means and how to relate to the fluctuations to correlations. Okay, so then we solve this. Okay, so now we are going to solve this Langevin equations. Okay, quickly. And yeah, so okay, so the Langevin treatments. Okay, so Langevin equations. So you can write this Langevin equations is m x double dot, right, equals to minus, let's say, alpha x dot plus ft, where alpha, just check this thing. So m divided is means that x double dot, yeah, alpha is 6 by eta r, so alpha is 6 by eta r, okay, because the eta is constant, r is constant, okay, so alpha is a constant. So now we solve this equation. Okay, so how to solve this equation? So just we multiply both side, multiply both side by x, we get that a x double dot equals to minus alpha x dot plus x f of t, right? And then we can written in more compact form that m derivative of x dot equals to m x dot square minus alpha x dot x f of t. So there are two line calculations. You can back calculations. You can do the back calculations just on derivatives and you get this thing. So now average over the times. Okay. So remember that average over time. So now we are putting average over time whole equation. That means that m ddt is x dot average m x square average, right, minus alpha x dot average plus x ft the average, right? So then okay, so here we will make on things that okay, so there is a x ft average, right? So if a and b are uncorrelated, then this AB average, can you tell me what is this? I'll discuss this in the first class. Okay, so if A and B are uncorrelated, then we can write this AB the whole average in terms of okay, so this actually written this in terms of A average and B average separately. Okay, if there is a no correlation, okay, between that A and B, two observables, let's say, and if there is a no correlation between A and B, so we can always write this AB the whole average is that AB average, A average times B average. Okay. So it's uncorrelated, it's importance. Okay, so we'll discuss so if I get time. Okay, so the what is the correlation and etc. So okay, yeah. So it's uncorrelated, then we can write this. So that means this x ft average, that means x ft, so this is a time dependent and this x, so they are uncorrelated, so that means we return this x average and ft average. Okay, so you make an assumption that ft is independent of the velocity, right? So ft is independent of the velocity as well as they are not dependent on particular positions. So ft appears randomly. Okay, so they are not dependent on where the position x, what is the velocity. Okay, so you can return this because they are uncorrelated, so you can return this way, and we know that this ft average goes to is 0, right? It's a random force, so the ft average is 0, so that means this quantity is 0, so these quantities vanish. So now this quantity, so this is actually calculated from the, this is actually the am v square average, right? So you know this is from kinetic theory. Okay, so from kinetic theory you know that what is this, is 3 kVt, right? Because half m v square is 3 by 2 kVt, so mv square is 3 kV, right? So then we are left with two equations. Oh, sorry, this is not 3, right? Because we are only considering x dot, so that means vx. So here vx square, this is a half kV. Okay, so only one direction, vx square, and not vx by vz. So in the previous case, we go that, yeah. So this vx vy vz. So each for half kV, and that's why you get a 3 by 2 kV. So this becomes crucial. Okay, so you know, use the equivalences there. So and then we can this quantity then finally becomes kV, right? So then we can write this. Okay, so one more point here is that, yeah, so if we write this x dot average, yeah, so now this becomes a first order equation, right? So ddt of x dot r average, and then this side is also x dot average, and all are constant. This goes to 0. So then we can solving this, we get this x dot average is a first order equation again. So we get some c constant times e to the power minus alpha t by m plus kVt by alpha. Right. So this is the first derivatives, and there is a, this x dot. So once we solve this equation, we get this. Okay. And this is a constant kVt, right? So okay, so this is a constant. Okay, so up to any point, any questions? Okay, so now we put the initial conditions that at t equals to 0, x equals to 0, no displacement, x equals to 0. So this keeps that c equals to minus kVt by alpha. Okay, so because this is a first order equations, okay, so we need only one conditions, initial conditions. Okay, so because there is a one constants, so first order differential equation gives one constant in the solutions. Okay, and we just need one initial conditions to get these constants. Okay, so we put that at t equals to 0, x equals to 0, we get the constants. Okay, so when we go into the second order differential equations in time, so that means we need two initial conditions in order to get a constant. So this is the property of the differential equations. Okay, so now we can put this into the above expression. So x dot average is that okay, so now, okay, so let's put in the this constant in the above expression. So what is that? That's minus sorry, yeah, so kVt by alpha 1 minus e to the power minus alpha t by a. Okay, so now we can write this x dot average, okay, in this way, that half derivative of x square average, right? Okay, so let's take that. Okay, so this actually x and 2 outside and x dot, right? So inside the time average, right? So when we derivative this x square, it's inside the time average. Okay, that means this gives 2 x dot, and this 2 taken outside. So okay, this is a constant, so that gives. Okay, so if we write this way, so then the equation becomes that derivative of x square average equals to 2 kVt by alpha 1 minus e to the power alpha t by a, right? So now just indicate our time, right? So both sides we indicate. So this is d, this is dt, so just indicate. we get a x square average 2 kbt over alpha. This time t, the integral over time, we get t minus m by alpha e to the power minus alpha t by, right? So this is a general expressions for the x square average. This is a general expressions of the x square average. Okay. So this is a general expression of the x square average. But how do we calculate it in the before that? What is the values of x square average? Just to, yeah. So x square average is 2 dt. Right? Is proportional to t. Right? So, but here is that this t and e to the power minus alpha t by n, a complex time dependence are there, right? So then we take a limit. If we take a proper limits, that means that let's say t is very less than equals to m by alpha, right? So your time scale is very less than equals to the m and alpha is a constant. Okay. So that depends on this the 6 by 8 r, right? So if we take these limits, that means this actually gives that x square average is kbt by m into t square. It's not t, it gives a t square in this approximations. Okay. So, but if we consider this t is very greater than equals to m by alpha, right? So your time scale is much greater than these values, then this x square average gives you 2 kbt by alpha times t. It gives a proportional. It gives a proportional to t. Okay, t to the power 1, right? So this is a general expressions of the x square average. Okay. So once we use the proper time regions, okay, and proper time scale, that is very greater than equals to m by alpha, we get this proportional to t. But when you do the opposite case, that your time scale is very small, then this is not valid. Okay, so this proportion goes to t square. Okay, right? So, but we calculated from the this that x square average is 2 dt from the probability distribution functions. Okay, we get that this, right? So that means 2d actually 2 kbt by alpha. If we just match two expressions, okay, so this expression 1, let's say this is 2, so we compare 1 and 2, we get this, right? And we put the alpha, and we get that the d value is kbt by 6 by eta r, right? So this is the diffusion constant. So that means that the diffusion rate. So what is the physical significance of this equation? Okay. Okay, so after any point it goes. Okay, so what is the what this equation tells that? So that means that the diffusion rate d describing the random fluctuation of the particle's position, random fluctuations. So random fluctuations of the particle's positions, right? So because we calculated that it's a random fluctuations and end up with these equations. Okay, so you end up with these equations, calculating from the random fluctuations. Okay, and taking a, if it is a random force, we end up these equations, and then we compare with the diffusion equations. We know this is comes from the diffusion equations. Okay, so this is comes from the diffusion equation, comes from diffusion equation. Okay, so big crucial here that this value come from the diffusion equations. Okay, so this is comes from the diffusion equations, and this is comes from the random force. Okay, we are taking a random force and modified the equation of motions and then calculating this x square values, right? And in this limit. Okay, so limit must be important. So in these limits, so that means the diffusion rate they describing the random fluctuations of the particle positions, okay, is related to the frictional damping. Related to the frictional damping alpha, right? So this alpha actually the damping, the drag force. Okay, so while we discuss this thing, yeah, so this is your alpha, right? 6 by 8 r. So this is a drag force, a damp force, and due to this damping, this velocity die out rapidly, right? So this is the diffusion d, diffusion constant, the diffusion rate d. Okay, that describing the random fluctuations of the particle to the fractional damping alpha, right? So this is an example of the fluctuation and the dissipations, they are related. Okay, so this d is kbt by alpha. Okay, the diffusion and this is a fluctuations alpha, so they are related. Okay, so this is an example of the fluctuation dissipation theorem. So it's an example of the, so this is an example of the fluctuation dissipation theorem. So how fluctuation related to the dissipation? Dissipation theorem. Okay. Okay, so this point is understood. Okay, so this is a very important concept that how the fluctuations, and first we calculate in the previous class, we calculate from the dissipation, the diffusion. Sorry. So yeah, the diffusion, they're kind of diffusion equations, and from this we are calculating the average, and we get this, end up these equations. Okay, so we end up these equations, and but today we calculate from the theoretical observations. Okay, from the physical significance, that what kind of actually what kind of force actually gives this kind of this x square average gives a non-zero values. Okay, so and the concept of existence of the random force. Okay, and then we, so this is actually comes from the dissipation. Okay, and the fluctuations. Okay, so the dissipation is comes from the diffusion equations, and the fluctuations is comes from the Langevin equations, and they how to relate that, this is calculate fluctuation dissipation theorem, one of the examples. Okay, so okay, so yeah, so this thing actually, okay, so you stop, and then we are going to discuss the week 5 assignment problems, and discuss some related concept to the problems. So okay, so first let me open the assignment, what problems are there. Yeah, so later if I get time, then we discuss about what is the fluctuation dissipation theorem and things like that. Okay, actually, and how the correlations actually what is the correlations. Okay, and yeah, so here I am making comment that if A and B are uncorrelated, then we get kind of things. Okay, so when they are correlated, then what happens? Okay, so this kind of things, if I get time, then I will discuss, but not today. Okay, so today we will going to discuss the assignment problems, assignment 5s. Okay, so okay. Okay, so let me think what to discuss. Yeah. Okay, so we're going to the discuss slowly. Okay, so just briefly recapitulates of the week 5 content that okay, so what we know from the classical point of view, the specific hits. So what do you know from the classical equipersons theorem? So from classical equipartition theorem. Okay, we know that E average is, I mean, from classical equipersons theorem, suppose we are considering a solids, right? And we consider the vibrations of the solids. Okay, so so let me think that which way I can discuss this. Yeah. Okay, from classical equipersons theory, how many degree of freedoms in a solids? How many degree of freedoms in a solids? Okay, consist of atom or molecules? Consist of atom and molecules. Atom or molecules. So how many degree of freedoms are there? 5? No, 2 atoms. Why there is 2 atoms? No, this is not the case. In a solids, the particle cannot move in any directions, right? So there is no translation motion in solids. So this is not a free, it is solids. Okay, so there have some kind of structures are there. So you cannot treat that the particle is independently motion, as in the case of the kinetic theory of gases. So kinetic theory of gases, there the particle can move any directions, right? But in solids, if the particle is position is fixed at a particular position, particular lattice, right? Particular position in the lattice, right? So they cannot move independently to any directions. Okay. So what can do that? Yeah, so if there is suppose atom or molecules, so they can vibrate in each of these 3 dimensions. 3 directions, right? But not the translates, right? So there is a no translation motions, only vibration and motion are allowed if some moderate temperature. So again, so the temperature must be important. Okay, so if the moderate temperature, that means the near the room temperature. So at moderate temperatures, okay, so the atom in a solids can vibrate, okay, and they can vibrate in any 3 directions, right? So if you consider a lattice, okay, so there are 3 directions. Okay, so let's say this atom, and there is a 3 directions. Okay, 3 dimensional lattice. So they can vibrate in this way, right? So they can vibrate in this way, right? And they can vibrate in in this way also. Right? In the 3 dimensions they can vibrate. Okay, so each vibrational mode gives how many degree of freedom? No, each vibrational degree of mode, there are 2 degree of freedom, right? Because once from the, so okay, so we'll discuss in the first class that if we write the energy or Hamiltonian, or so this is, there are some half m x dot square plus half k x square, right? So this kind of things. So the both are gives half kVt. Because these vibrations we are considering that there is a spring, and due to the spring we consider potential energy, and this potential energy gives a half kVt, and due to this vibrational motions, okay, so this gives a half kVt. This is not a translational motions, okay, so it's a vibrational motion. So each vibrational mode gives a 2 degree of freedom. So there is a 3 vibrational modes, sorry, 3 modes in the 3 direction. Okay, so this total gives a 3 into 2 6 degree of freedom at moderate temperatures. That means T, let's say, nearly equals to room temperature, right? 300 kelvins. This kind of this region of temperature, right? Around the room temperatures. We are considering that only 6 degree of freedom. Okay, so that means the E average is 6 into each mode half kVt, right? So from equipoison's theorem is 3 kVt, right? If there is a any number of molecules, right? So that means the 1 mole, okay? So then is total that so it's multiplied by just by Na. So it's kV Na gives the R, that means the 3 RT. Okay. So now the specific heat CV is actually delta E average over delta T. So how to know these equations? Okay, so this actually comes from the thermodynamics. So when we study the thermodynamics later part of this course, so we will see that this equation come. Okay, so yes, yeah. So normal modes, there are 3 because in the 3 directions. Okay, so that's why there are 3 normal modes, and each normal modes. So actually, I am saying the mode means the normal modes, right? So each mode we gives a 2 degree of freedom, and 3 normal modes in the 3 direction, it gives a 6 degree of freedom. It's now clear, right? Yeah. Yes. Normal modes is 3n. That's why when we consider n molecules, we multiply it with Na, right? That is actually 3Na. Okay. So if there is n molecule, so you multiply it with n. So that means you take that the normal mode is 3Na times 2 is 6Na. So end up with this. Okay. So this gives a 3R, right? So this is a Dulong-Petit's law. But this is a Dulong-Petit's law. Dulong-Petit law. But this is a not universal. So this is only true for the moderate temperatures, right? Or maybe we are considering that the high temperatures kind of thing. At low temperature, what is the behavior? So previously, sometimes I told that at low temperatures the physics might be different. Okay, so then at low temperatures, so if it let's say at low temperatures T going to be small. Okay, so then the Einstein. Okay, so why we know that if low temperatures the physics might be different, right? But experimentally, observe, so experimentally observes that this Cv must be goes to 0 as T goes to 0, right? So if T, the temperature, goes to 0, the Cv must be goes to 0. But from these equations, you cannot tell that the T goes to 0, Cv goes to 0, because Cv is a constant. There is no temperature dependence. But experimentally observe this. Okay, so this is actually the third law of thermodynamics. So when you study the thermodynamics, and there are three laws: first law, second law, third law. So the third law of thermodynamics tells that the T goes to 0. So when the T goes to 0, the Cv must be goes to 0, and experimentally observe this. Okay. So then, so that means at low temperatures that are near 0. Okay. So the physics might be different, right? So then the Einstein theory of specific heat comes. Okay. So Einstein theory of specific heats. So in 1907, okay. So I think, and the class are also described this thing. So in 1907, the Einstein specific theory of heat set. Okay. So they calculated in that the cavity vibration. Okay, and so I'm not going to the derivations. Okay, so I also derived in the class. Okay, so just look it into the lectures. Okay, so then I end up with this equation that Cv is 3r times x square e to the power x by e to the power x minus 1 by considering a cavity radiations. Okay, so yeah, so cavity vibrations, sorry, cavity radiation, the cavity vibrations. Okay. So atomic vibrations in a solid is equivalent to a electromagnetic vibrations in a cavity. Okay. So these equivalents, and we end up with these equations that Cv, and there is a quantum mechanical calculations up there. So once you done this, we end up with these equations. Okay, so Cv is, so where x is the theta e by t. So this is theta actually the Einstein temperatures, right? So this theta e is Einstein temperature. Okay, and T is the usual temperatures. So Einstein defined a temperatures. Okay, that is called a theta e. Okay, and this is the Einstein temperatures, right? Yeah. So now here let's consider that T is very greater than equals to theta e, right? So at temperatures, high temperature region. So this is actually the high temperature region. Okay. So at high temperature region, okay, that means that this T is very greater than equals to theta e. Theta is the characteristics temperatures of this theory, Einstein theories, and there is some characteristic temperature that is called the theta e. So the usual temperatures is very greater than equals to this characteristic temperatures called the Einstein temperatures. Is T very greater than equals to theta e. That means you are in the high energy, high temperature regions. So that implies that x is very less than equals to 1. Okay, so this Cv is nearly equals to 3r, right? So if x is very less than equals to 1, then we just expand this. Okay, e to the power x, and this we have get this, right? Because x is very less than equals to 1, then we can take this kind of things that e to the power x is nearly equals to 1 plus x, right? And then so this x square e to the power x, this is nearly equals to x square. Okay, and the denominator is that e to the power x minus 1, so it is x square. So x square cancel, so it's just 3r, right? So that means they agree with the Dulong-Petit's law, right? At high temperatures or the moderate temperatures, Okay, and this gives a 3r. So Einstein modified this specific heat, and if the temperature is very very greater than equals to Einstein temperatures, so this also gives a 3r. So now what is happens if T is very very less than equals to theta, right? So theta Einstein temperature, let's say the order of 50 Kelvin, right? So for better clarifications, that theta is, let's say, order of 50 Kelvin. So Einstein temperature is order of 50 Kelvin. So then this 273 Kelvin or 300 Kelvins at room temperatures. So this is very very greater than equals to this 50 Kelvin, and this gives a 3r. But if T is very very less than equals to theta, that means let's say T now this is a low temperature region. It's very low, 1 Kelvin, 2 Kelvin, this kind of things. So it's a low temperature region regime. Okay. So this implies that X is very very greater than equals to 1. It is CV is 3r x square e to the power minus x. Okay. So how to know that? So when x is very very greater than equals to 1, so this e to the power x minus 1 is just like e to the power x. So e to the power x minus 1 is just like e to the power x. Okay. And we can square that x square e to the power x by e to the power 2x. Okay, so this gives x square e to the power minus x, right? So these things. So now we put this in terms of the temperatures, that 3r at high low temperatures. So this region 3r. So just make this. So these temperature regions, where I down this 3r times x is what is the x is theta e by t, theta e by t, the whole square e to the power minus theta e by t. Right, but this is again not a correct at low temperature. So what we observe, so experimentally we observe that at Cv goes to 0 as t goes to 0, right? So if we in this case we put t goes to 0, the Cv not goes to 0, right? Because there is a 1 over t square there, so this is not exactly correct. Okay, so then the new theory. So okay, so another thing that here we can claim that at t goes to 0, Cv goes to 0 roughly, but experimentally again the more specifically observes that Cv is proportional to Tq at low temperatures. Okay. So it's a power law like distribution. So it's proportional to Tq. Okay. So power law means that when certain quantity is depends on the power of some variables. Okay. So this kind of is a power law. So Cv is proportional to Tq. It's a power law kind of distribution. So it's proportional to t to the power some n, where in this case n equals to 3. So it's to the power. It's not a exponential like distribution in the case of Einstein theory. Okay? So it's a power law distributions. And experimentally observes that if we plot the experiment and then we can fit into this data, we gave this cube kind of power law kind of distribution. So they are low temperatures. And then from this case also that Cv goes to 0 at t goes to 0. So then the new theory comes. New theory comes into the picture. It's called the Debye theory of specific heat. Debye theory of specific heats. Right? So you map that what kind of corrections one by one happens. Okay. So any questions so far? Okay. So then the divide theory of specific and we have calculated rigorously. Okay, so calculate density of states and then we can calculate the specific heats. Okay, so I'm not going to the derivations of this device specific heat and just writing the formula. Okay, so the formula is that we end up with the equations when we calculate in this rigorously. Okay, I think in the discussion the week 5 lectures are also calculated this thing rigorously. Okay, so just just go through this. Okay, and this CV yeah, so CV is just a we get this a complicated expressions like 3r over 12 over xt the cube. Okay, so 0 to xt x cube to the power minus x, right? There is a dx 3xt. Okay, so then we define a dy functions. Okay, it's 3r d of xt. Okay, this is a dy function. So this is the whole thing is equals to this d. Okay, so this is a dy function. So again the xt is just similarly from the Einstein case, but in this case the divide temperature theta divide. Okay, so in the Einstein case we are indicating that the theta e Einstein, in this case theta d is the divide temperatures. Is the characteristic temperature of this theory. Okay, divide temperature. So the characteristic temperature of this theory, right? Okay, so again we are going to the high temperature limits. That means T is very greater than equals to theta d. In the high temperature limits, that means again that the xt is very less than equals to 1. So this gives, okay, so this gives a CV is nearly equals to 3r. So that means that divide theory also follow the Coulomb-Petit's law at very high temperatures. Okay, so at high temperature DMs, Einstein theory, divide theory, and you know that from kinetic theory, all are the same, right? But at low temperatures, the kinetic theory cannot explain at a low temperatures, so we have to modify it. So Einstein first modified and then divide, right? So this xt is also called the characteristic length of the solids. Sorry, characteristic temperature. Okay, so theta d. Okay, theta d is the divide temperature, is the characteristic temperature of the solid. Characteristic temperature of solid. Because this is the best theory, divide theory, to describe the solid specific heats. That's why this is called the characteristic temperature of solids. Okay. So okay, so in this high temperature regions, the goes to same. But what about the low temperature regions? T very less than equals to theta d. That means x is very greater than equals to 1. Okay. So then we calculate yeah, so when this x very greater than equals to 1, that means so this e to the power xt minus 1 is equals to e to the power xt, right? And this 3xt. Okay, so we end up with this equation that 12 over, okay, so roughly it should be that 12 over xt cube. Okay, so roughly we are not considering any constant but dependence of this xt, and this 0 to, so if xt is infinity, so we take this limit, the xt is very large, so we take this limit goes to infinity. Okay, otherwise these integrations cannot solve. Okay, so dx, so when you solve this integral, it gives a constant value. Okay, so this gives a constant value h pi to the power 4 by 15. Okay, so that means and the other thing is that so yeah, that's all, and other constants are there. So this is just 1 over xt cube, right? So that means if we put in terms of written down in terms of temperature, that means Cv is some constants. Okay, so if we write the exact constant, that 12s are pi to the power 4 by 5, and xt is the theta d by t. So xt means the theta d cube into d cube, right? So at low temperatures, so at low temperatures, we have found that Cv is exactly proportional to d cube, right? So this is the d by d cube law for low temperatures. So this is a d by d cube law. Okay, d by d cube law, and this is works well for most of the solids. Okay, so now you may ask that so this is again so again we have to go into the very low temperatures. Okay, so then the electron specific heat also contributes. Okay, so when we go into the very low temperatures, okay, so means that the ultra low temperatures. Okay, so this d by 2 cube again says some characteristic length is theta d, and the temperature must very less equals to this characteristic temperatures. But when we go the ultra low temperatures, okay, so it's very low temperatures, then okay, so this works for most of the solid. Okay, so works well for solid. Works well means that the we compare with the experimental results. Okay, theory, when we theory compare with the experimental, then this works well. Okay, but when we go into the ultra relativistic case, ultra relativistic, not ultra low temperature case. So when we go into the so at ultra low temperature, right? So then the free electron specific heat also contribute. Okay, so free electron specific heat also contribute. Okay, so then the total specific heat becomes, and this is crucial for metals, right? So then so this is crucial. Okay, so this the free electron specific heat this is crucial for metals, crucial for metals. Okay, and the Cv is that some ATQ plus BT. So this kind of things. Okay, and at so this is a total, right? And at ultra low temperatures, that the free electrons, so free electron specific heat, let's say Cv and free electron. Okay, free. This is actually proportional to temperature. So there is rigorous derivations for this, but we are not going into the derivations that how this electron specific heats, free electron specific heat proportional to temperatures, right? So just make a note that at this point that Cv the specific heat or electrons is proportional to temperature, free electrons. Okay, so we will later the rigorous derivations we'll discuss, but yeah, so at this point we just make a note that this thing and the total specificates that, okay, at low temperatures. Okay, okay, so now yeah, so almost there. Okay, 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 so now we're going to the assignment problems. So once you know that this formula, okay, we just put in the formula. Okay, so I'll show that how to calculate. Okay, so let's say so the questions one. So calculate the temperature, just address the Einstein. Okay, so calculate the values of the Einstein frequency for a solid for which the Einstein characteristic temperature is, let's say, 273 Kelvin. Okay, so calculate the value of Einstein frequency for a solid for which the Einstein characteristic temperature is 273 Kelvin, for which the Einstein characteristics temperature is 273 Kelvin. Okay. So okay, so in this problem we are assuming that the Einstein theory is described well for the solid. So and we calculate the, okay, so calculate the value of the Einstein frequency for a solid, and the given is the Einstein temperature. So what do we know that we know that the Einstein temperature theta E, right? So Einstein temperature theta E is H nu E by kb, right? So this is the Einstein temperatures, okay, and so this is the Einstein frequency H nu. Yes, this is just a, so E equals to, if you know that the energy E equals to kb, right? And this energy, when we consider Einstein quantum theory, that this is actually H nu, okay. So H is a Planck constants, okay. So and nu is a frequency, okay, of the quantum modes, and this gives it cavity. Okay, so this is a T is a temperature. So for Einstein case, so this temperature is, the characteristic temperature is theta E, and the corresponding Einstein frequency is H nu E by K. Okay, just roughly you can. So this H is a Planck constants. Okay, so E is a Planck constants. Planck constants value is 6.626 into 10 to the power minus 34 joule second. Okay, yeah, so this value is, and kb value, if you know the what is the kb, it's a Boltzmann constant. It's a Boltzmann constant. It's 1.38 into 10 to the power minus, yeah, so 10 to the, yeah, 10 to the power minus 23 joule per Kelvin, right? Yeah, so once you put this and you know the theta E, I am already tell that the Einstein characteristic temperature is 273 Kelvin. So what are we going to assume this thing? Okay. So what is the order? The given is that theta is 273 Kelvin, and we just put in the formula, we calculate, right? Okay, so we are calculating the order. Okay, so is 10 to the power minus 34. So okay, so we are calculating in order that 273 means that 10 to the power square, and kb is that 10 to the power minus 23, and age is 10 to the power minus 34. So its order, if you calculate the which orders there is, okay. So yeah, so 21 and 21, yeah, 16 to the power 32. So in this order, roughly, okay, the hertz. So we exact calculates, okay, but the frequency is the roughly 10 to the power 13 hertz, okay. So okay, so next is that okay, so again, so in this case the temperature is given, Einstein temperatures, and we calculate the Einstein frequency. Okay, so then we can opposite, we can ask that what is the Einstein frequency, sorry, what is the Einstein temperature when the frequency is given. Okay, so using the same formula we can calculate. Okay, so next is that okay, so suppose the next is that suppose the Einstein temperatures of a material is so let's say the Einstein temperature. So if Einstein temperature for a material, it's let's say 70, sorry, it's let's say 50 Kelvin, okay, and compute the values of Cv at temperature let's say 25 Kelvin. So compute the values of Cv. So compute Cv at, let's say, temperature T equals to, so compute Cv at temperature let's say 25, and okay, so this calculate the Cv at different temperatures. So that characteristic temperature is the Einstein temperature. So this is the different from the usual temperature, right? So then we know from, okay, so the solution is that we know that the T is 25 Kelvin and theta is the characteristic temperature is 50 Kelvin. So we define that X is theta E over T, so that means 2. Okay. So here X is 2, and now we put in the formula, what is Cv, yeah, so Cv is this 3r x square e to the power x. So yeah, use full formula because you are not cutting any approximation that x is very very greater than 1 or x is very very less than 1. So you know that x is 2, so here use full formula, that 3r x square, sorry, yeah, so x square is 4 e to the power 2 x and e to the power 2 minus 1. So you get some value, you know the values of r. Okay, so you calculate this. Sorry. Okay, so you calculate this. So the, what is the values of r? R is at 8.314. Okay, so joule per mole per kilo. Okay, so what is the values of specific heat here? Okay, what is the unit of x? Yeah, so if you calculate this, 18.05, okay, roughly, okay, so 18.05. What is the unit? Yeah, because this is a unit of r, there is no other quantity with the dimensions, right? X is dimensionless, right? It's a ratio of the temperatures, right? So x is dimensionless, and all the other, so this is just a constant, so there is no dimension, so only dimension is that from r. So the unit of r is actually the unit of c, right? So also you know that Dulong-Petit's law, Cv. just a 3R, right? So dimensionally, if you go into the lower temperatures, your dimension is same, right? So the quantity cannot change with the another quantity, right? So it describes the at higher temperatures gives the that things your lower temperature dimension must be same. The quantity is the same, right? The observable is the same, the field. So the unit is just a joule per mole per Kelvin. Okay, so again, if you add some to observables, right? So if we add only when the dimension is same, right? So different dimensions cannot add or subtract. Okay. Okay. So similarly for the dy case, you also calculate. Okay. So for dy case, let's say the theta d is given, and so this is a similar way you can calculate for dy case. Okay. So let's say is theta d is some Kelvin, 30 Kelvin, or you calculate the specific heat Cv. Let's say at T equals to 10 Kelvin, right? So just put it to the formula and we get the answer, right? Yeah. So just put into the formula, okay, and we get the answer, right? So what is the formula? That formula is that the 4 pi to the power 4 by 5 3R. Okay. Okay. So in this case, yeah, let's say this is things okay, theta d, the characteristic temperatures. Okay. And we are using this limits that theta d is the small temperature because T is 10 Kelvin and theta d equals to 30 kelvins, 300 kelvins. Then we can use this result, right? So this limit, so you can use this result. So you can use these results. So if you use these results, okay, so this 4 pi to the power 4 and this is 3 pi, okay, so this is actually gives it 12, okay, and this R, okay, and T by theta d. So now you know R and you know T is 10 Kelvin and theta d is 300 Kelvin. We get the results, right? Okay, so I think you calculate these things. Okay. So now, okay, this one is clear, right? Because if you calculate explicitly, then the calculation becomes complicated. Means that if we use this formula, okay, if we use this formula, okay, so this is the you have to do numerically, right? So the integrations performed numerically. So that's why if there is a data given, thus that we can use this any kind of approximations, these approximations, or you can these approximations. Then the calculations become ideal. So you can do easily. So that's why the data is given in such a way that so we can use any of these two approximations. Okay. So in this case, let's say theta d is given 300 Kelvin and t is we have to calculate the specific heat at 10 Kelvin. So you can easily use these approximations. You can easily use these approximations and you can just put in the formula. Okay. But in general, this is not true. So suppose if I given that theta d equals to 30 Kelvin and you calculate the specific heat at t equals to 10 Kelvin, then this kind of assumption is not anymore. Okay. So we have to do explicit calculations, okay, and solve the integration numerically. Okay, so these things are there. So now, yeah. Okay, so now we are going to discuss, yeah. So one or two questions are left. Okay. So now the second question was, let's say for a certain metals. Okay, so for a certain metal. So the velocity of the transverse waves, okay, so I think the velocity of the transverse waves, okay, is one third of the velocity of the longitudinal waves. Okay, so waves. So what is the Debye frequency? Then what is the Debye frequency? Right, so this is your question. Yeah. So how to calculate the Debye frequency? So again, you know the formula. That's the Debye frequency is yeah, that's good. Yeah. So this is right? Mu cube. What is mu? Yeah. No. There is no cube. This is just Debye frequency nu d. So I think there is no cube. Let me check. Oh, 1 minute. Yeah. I think. Okay. Let me check. Just a minute. Okay, so let's change the dimensionality. Okay, so the n by v, okay, and the frequency and the velocity. Uh, yeah. I think there is a cube. Yeah. Yes. Okay, so once you start, you just calculate the dimensionality. Okay, so ct is the velocity, so it's a meter per second, right? So then this and the volume is just a meter. Okay, so that means there is a second cube are there. Okay, so they compensate with the Hertz cube, right? So when you start, just calculate the dimension and yeah. So okay, so then yeah. So in this case, that c the transverse waves is one third of the velocity of the longitudinal waves. So that means ct is one third of cl, right? Yeah. Am I right? So the transverse waves is one third of the velocity of the longitudinal waves. Yeah. So now we put, and once you know, okay, so now there is a one unknown is n by v, right? So let's say this is specified. Okay, so let's consider n by v is 6.02 into 10 to the power 28. Okay, so also no, we can calculate this mu, right? So there is no problem. because all the quantities you have to know. Okay, so once you know the CL, sorry, once you know CL or CT, any of one of these. Okay, so let's say CT is 6374 meter per second. Yeah, so then I think the complete data is given, so you can calculate. Yeah, so there is no problem, right? Okay, so now, okay, so what is that? Okay, so what is the van der Waals equation substitute? So van der Waals equation of states. Okay, there is just kind of discussions. Okay, I think there is no more problems you have to discuss. Okay, so what is the van der Waals equation substitute? So next we start from this real gas. Okay, and yeah, so next day we'll start from the real gas and do some problems. Okay, related to the real gas with some potential. So okay, so van der Waals. Okay, so let's briefly discuss about the van der Waals and then we stop there. So van der Waals equation of states. Okay, so the van der Waals equation of states is that that for 1 mole it's a P plus A by V square and P minus B equals to, let's say 1 mole is RT, right? So that the B, the dimension of B, okay, again, so when we add the two quantities, right? So this must be the same dimensions. Okay, so when we add subtract B and minus B, so the dimension of B and the dimension of B must be same. Dimension of A by V square, dimension of B must be same. Okay, so dimension of B, so we written in the dimension in this form that P, that means the dimension of B and the dimension of A by V square must be same. Dimension of B, dimension of B must be same. Okay, so when we add or subtract any two quantities, okay, so the dimension must be same. Okay, but for not the case for multiply and divide. Okay, so these kind of things, and so in this case that the so these equations actually tells that it's a modified versions of the ideal gas equations. Okay, and this is a pressure. So in this case, if you write the pressure, okay, it's just a RT by V minus V by A by V square, right? So this is a modified. So what do you know from the ideal gas? From ideal gas, you know that ideal gas, we know that this P is actually RT by B, right? Okay, so that means, so if we consider a molecules, they have not a point like objects, they have some structures. Okay, means that they acquire a volume B. Okay, so B minus B, so B is a, again the same dimension, so they acquire a volume B if all the molecules are in theories that consider a they acquire a volume B, so then the volume becomes a modified, okay, for the real gas. So this is the real gas situations for the van der Waals gas, let's say. So the volume is V minus B, so the volume, actual volumes, okay, the available for the motion of these molecules, okay, for on molecules, okay. So available for the motions of these on molecules are V minus B, because the so each molecules acquires a volume B, right? So the available is the V minus B, and so then when with this the available volume is V minus B, that the pressure must be increased, right? Because volume decrease means pressure increase, so pressure is actually P plus A by V square, right? So pressure will be increased and volume will be decreased, and this gives kind of equations. Okay, so we'll discuss more about the real gas, mostly the van der Waals gas in the next session. Okay, and so yeah, so we have to do a typical examples where this V, B, A all are the specifiers. Suppose you have specified the temperature T, let's say 273 Kelvin, and you have to give an A and B. Okay, it's a certain values. Okay, so let's say 0.082. Okay, so 0.082 not that. Okay, so we can choose any values. Okay, so choose some value A and B and T. So these are the specified. Okay, given. So these data are given. Okay, so then we can calculate the pressure in the van der Waals gas and the ideal gas, right? So can you say namely that which is on is bigger? So if you compare that, P equals to RT by V, but in this case P equals to RT by V minus V into minus A by V square. So the van der Waals gas, the pressure is less to the ideal gas, right? So you can say naively, but you have to do exact calculations and then we can say, right? So you have just take this value T equals to 273 Kelvin and take A and B. Okay, and we calculate these things. Okay, so if we choose a proper values of A and B, we can calculate and compare with the P1 to P2. Okay, so if this data is specified, so you can calculate and you know the R. So we'll discuss more about this in the what this equations actually tells. Okay, so what these equations actually tells. Okay, so this we'll discuss in the next class. Okay, and start from the real gas and then do some problems. Okay, on the real gas. Okay, yeah. So far, any questions? Okay, so okay, I think the assignment problem is already done, and yeah, so no more things left for today.
So it's a different type of data. One way of negative.
Okay, so then we will see in the next series. Okay, thank you. Bye bye.